Welcome everyone to chapter 20, which is all about thermodynamics, right? And we may not know this, but thermodynamics is an entire semester of chemistry if you were to get a chemistry major, right? It is part of physical chemistry. It's one of the two semesters of physical chemistry. And thermodynamics is based around basically one main equation that we're going to see a little bit later on. And then from that equation, we can manipulate it in several different ways. But if we can get that equation down and understand the concepts of each one of them, then we should do really well in this chapter. I will also point out that of all the chapters in Chem 2, this one's probably going to come up the most on your final exam. So make sure that you definitely go back and go over these slides again before taking your final exam, as a very large portion of it's going to be based on this chapter. So the first podcast that we're going to go over here in chapter 20 is all about going to be spontaneous reactions. All right, what makes a reaction spontaneous? What's the definition of a spontaneous reaction? Right, we can just kind of think about a spontaneous reaction. We have an idea of it, but we're going to talk about it a little bit more in our chemistry sense of what makes a spontaneous reaction versus other types of reactions take place. So when we're talking about whether a reaction is spontaneous or not, right, what we want to do is think about this by asking ourselves one question. And that question is, right, as it states there, will a reaction occur by itself at a given temperature and pressure without us exerting any outside force? And as we look at this, I'm going to tell you that we have one caveat to an outside force that we can add to a reaction to get it started, which is a spark. But anything else, right? We can't sit there and, stir it. We can't sit there and heat it. We can't sit there and cool it down. We can't change anything about the reaction. Basically what happens is we can mix a couple things together and see if I just walked away, if I come back, will a reaction have taken place? If a reaction will have taken place by me just walking away from it, then we're going to say that that reaction is spontaneous. And this question's asked by, it says here, synthetic chemists, metallurgists, engineers, really anyone who deals with chemistry at all wants to figure out whether a reaction is spontaneous or not. If a reaction is spontaneous, it is cheaper for us to be able to do that reaction. Right? Think about it. If I took two chemicals together and I mixed them into a beaker and I walked away and my reaction happened and I didn't have to do anything, that's pretty cheap. All I had to do was, have a beaker and mix a couple chemicals together. But if I took those chemicals and instead of me just mixing them together, what I had to do was I had to mix them for 15 hours and then I had to heat it up and have it melt for 6 hours, and then I had to cool it down and do all these things. Well, now I'm adding in us putting in time management, like, having humans do this, but we're also adding in things like electricity and, those sorts of things. Those start to cost more money. So spontaneous reactions are cheaper. So anyone that deals with chemistry is always asking themselves, is this reaction spontaneous? And if not, then what do I have to do to maybe cheapen this reaction itself? So I've brought up the idea of if a reaction is spontaneous, we don't have to do anything to it. But if it's not spontaneous, we might have to, heat the reaction up, right? Which takes some electricity into like maybe a hot plate, or maybe it takes some fire into a Bunsen burner to heat it up or whatever. Remember, right? We've talked about the transfer of heat before. That came all the way back a long time ago in Chem 1. In our book, it was in chapter 6. Where we talked about something that we said was thermochemistry. All right, thermochemistry was our jumping off point for this entire chapter that we're going to call thermodynamics, right? And so thermodynamics is going to deal with the heat and energy effects, but it's not just going to take into the thermochemistry that we learned in chapter 6. In chapter 6, we learned about enthalpy change, right? That delta H. Remember, and we have a positive delta H. We said that that was an endothermic reaction. If we have a negative delta H, we said that that was an exothermic reaction. Right? Remember those because they're not going away, and we're going to use them all throughout this chapter on your next exam, on the final exam. Make sure you remember those signs for those, but we're going to expand upon our enthalpy changes as well. Right? And so, right, that is one of the things that we can decide might make a reaction favorable or not. if we think about enthalpy change, if it's exothermic, if it's giving heat off to the surroundings, that's likely going to be a spontaneous reaction, right? If we think about it the opposite way, if we have an endothermic reaction, right? We think about an endothermic reaction, we have to put heat into the system. Well, usually for us to put heat into the system, right, we're having to, say, put a Bunsen burner and heat it up, or put it on a hot plate and use electricity. That's not spontaneous. We are physically affecting that chemical reaction by adding heat to it. So usually, and I'm saying usually for a reason because we're going to see in a little bit, but usually, right, endothermic reactions are not spontaneous, and usually exothermic reactions or negative delta H reactions are spontaneous. Now we'll see that it's not always the case, and we'll see why as we go through the chapter. But just think that, usually that is the case, right? It's a good point for us to kind of have a grasp of, all right, yeah, that makes sense. All right, and so what we're going to do then is with the thermodynamics, we're not only going to look at that as a factor, but we're going to find what other effects cause a reaction to maybe be spontaneous or not. Right? And once we figure out what all the effects are, we're going to define something that'll tell us whether a reaction is definitely spontaneous or not just if it's usually spontaneous or not. So as was stated in our previous slide, right, when we were starting to bring up that enthalpy change that we saw in chapter 6, right, again, as this slide is pointing out as well, right, just kind of me talking in the last slide, and this one's going to be pointing it out in a written style, is that our enthalpy change, right, we have endothermic and exothermic reactions, and when we have those reactions, right, remember that our exothermic ones are the ones that we said tend to be favorable, right? They're likely to be favorable. Again, it doesn't mean that they are. So because our enthalpy change won't tell us whether or not we have a spontaneous reaction for sure or not, then we started thinking about it. We decided we got to come up with maybe something else that might tell us whether a reaction is going to be spontaneous. So we decided to define another term that we're going to give the symbol of delta S. All right, S is entropy, right? Not enthalpy, but entropy, E-N-T-R-O-P-Y, entropy. And delta S then would be the change in S, because remember, anytime that we see a delta symbol in chemistry, right, that means that we have a change in something. So we have the change in S. All right, now again, once we came up with our entropy, and we'll talk about what entropy is as we go along, but what we found is that a positive delta S means that we are likely going to have a spontaneous reaction, but not necessarily. So again, that didn't solve our problem. So negative delta H and positive delta S are likely spontaneous. All right, but it doesn't mean that for sure. All right, so then we decided that we needed a third thing to help us define whether these were spontaneous reactions or not, which we came up with as delta G, which is the change in free energy, or the Gibbs free energy. All right, and a negative value of delta G, notice that it says will be spontaneous. Negative delta G, right, must be spontaneous. And I'm writing on here at a funny angle, so as you can tell, my writing skills are not that fantastic. But once we start working some sample problems, I'll lay it down and I'll write a little bit better. All right, so now it's time for us to then figure out some chemical reactions that are spontaneous, and that'll lead us into then looking at the enthalpies, entropies, and then those Gibbs free energies to talk about, how they are actually spontaneous. But first, I want us to just kind of think about everyday things that we kind of come across and just, our experiences in life. So we're going to do this, and then I have some sample problems as we go along as well, where we can just kind of talk about, hey, does this make sense or doesn't it? So everyday spontaneous processes, right, are things that take place without us affecting them, right, without an outside force. And again, the one that we could have is a spark. So I have 3 examples on here. I have an ice cube, right? So I have the solid water there as my chemical equation down below that. right, becoming liquid water. So our ice cube is melting in a glass of water at room temperature. So I've got my glass of water here, right, and I've got some ice cubes up there. And we know at room temperature, if I come back and say 30 minutes, some or all of that ice will have melted, right? That just happens without me doing anything to that ice. If I walk out of the room and I come back, it'll have melted. Next up is I have a mixture of hydrogen and oxygen, right? All right, so hydrogen plus oxygen, if I add a spark to that, that's the one thing I can do, right, is going to have a combustion reaction, which will turn into liquid water and a whole bunch of fire, right? That's a combustion reaction. Well, once I set that spark off, if I fill my entire room with hydrogen and oxygen, I set a spark off in one little corner, the whole room's going to blow up. All right, so we're spontaneously is going to go until we run out of the fuel. All right, and then lastly, I've got some iron reacting with some oxygen to produce some iron 3 hydroxides there. All right, notice that this is the formation of rust. All right, so what I want us to see is that, right, having a spontaneous reaction does not necessarily mean that it's fast, right? If I take a, hammer and I set it outside and I come back in 30 minutes, I'm not going to see any rust on that hammer. But if I come back, say, like 5 years later, I'll probably see some rust on that hammer, right? And so it doesn't necessarily mean that it's fast. It just means that I left it alone and the reaction still occurred on its own. So on the previous slide, we talked about the fact that we had our example of, our rusting, which is a slow reaction, but it's still spontaneous. And we had hydrogen plus oxygen, right, in a combustion reaction, which happens really fast, right? If we think about that one, just think about like the Hindenburg explosion, right? If you don't know that one, then just Google it. Come on, right? That happened really, really fast, right? I mean, that's a quick reaction. So, but we need to see that spontaneous doesn't mean that it has anything to do with how fast or slow the reaction is. It doesn't have anything to do with the rates of our reactions. So remember the first chapter that we did in Chem 2 is all about rates of reaction. That doesn't apply to whether a reaction is spontaneous or not. The speed of it doesn't matter, right? The next little bullet point there says that if a reaction is spontaneous in one direction, it is non-spontaneous in the other direction. So if I take hydrogen and oxygen, right, and we apply that spark, it's going to turn into liquid water and a whole bunch of fire. But if I take a glass of water, right, I got my glass of water, my ice still hasn't completely melted because this is very recently from the last time I showed it to you. If I've got my glass of water, right, it is not just breaking apart into hydrogen and oxygen gas all the time. It's just remaining as liquid water. So that's non-spontaneous. To turn it into hydrogen and oxygen, I can do that, right? Something called electrolysis, which we'll learn about in chapter 21, where I put electricity through it, but that's me having to put electricity through it in order for that reaction to take place. That's not spontaneous. Spontaneous happens all by itself, and water doesn't decompose by itself. So we're never getting away from equilibria in this class. And we're going to talk about equilibria constants as we go through this. But let's first off kind of bring up the reminder of what equilibria is that, right, equilibria is where our reaction, right, has both products and reactants, and the concentrations of those are not changing over time. All right, well, a spontaneous reaction happens because it's not at equilibria, and it's trying to drive our reaction towards being at equilibria. It's going to make more and more products until we actually reach the equilibria point, right? And then so a non-spontaneous reaction is going to move away from equilibria. That's us forcing that reaction to move away from equilibria, right? If I had water and I was forcing it to turn into oxygen and hydrogen gas, right? Well, that's not where it was at equilibria. It was already happy at equilibria, just sitting there as liquid water, right? But we're forcing it to go away from that by introducing an outside force. So spontaneous reactions want to go to equilibria. Non-spontaneous are moving away from it. Okay, when we're talking about whether something is spontaneous or not, right, whether it's a reaction or just, something like a boulder rolling down a hill, right, that boulder sitting at the top of the hill has a whole bunch of potential energy. When it rolls down the hill, right, once it's at the bottom of the hill, it's sitting there, it doesn't have nearly as much potential energy as it once did, which means that it has lost energy. most of our spontaneous reactions are also going to have a decrease in energy. Again, this says most or many, not all. Right? So if we think about our exothermic reactions, right, they decrease in energy as the reaction takes place. Because remember that an exothermic reaction has our reactants are going to be higher in energy than our products are, right? And so as the reaction takes place, the reactants will make products, they will have lost energy that's gone out to the surroundings. So they've actually decreased in energy. And just like our boulder, right, for many or most of our spontaneous reactions, they're usually or typically exothermic, right? Which also means that, right, for our non-spontaneous reactions, they're usually endothermic, right? And then another way of saying that on the very bottom bullet point, the reverse is also true. Exothermic reactions are usually spontaneous, but again, they're not always spontaneous, right? There are some really easy ones that we can see right away that break that rule. We've already seen one. One really good way that we can see that, right, not all exothermic reactions are spontaneous and not all endothermic reactions are non-spontaneous. It's just looking at a phase change. We've seen this one before when we've got our solid ice turning into liquid water, right? Remember, this is actually an endothermic reaction at room temperature. If I take a hunk of ice and I set it, on the table and I leave and I come back, it's going to melt, right? But that's actually an endothermic process because energy is coming in from the surroundings, right? It's having to come in from the surroundings, right? From the air in the room into the ice to melt it. That's endothermic. And yet it happens spontaneously, right? I put the ice on the table, I walk away, and it happens. So that reaction is spontaneous even though it's endothermic. We can also change whether a reaction is spontaneous or not, sometimes by changing the temperature. Remember, the definition of whether it's spontaneous or not is at a given temperature and pressure. Is it spontaneous or not? So here I've got some calcium carbonate, and it has an enthalpy change of 178.3, right? And that's positive. And when that's positive, remember that means that it is endothermic, right? And so we've got this endothermic reaction as it's written. Now, that reaction, right, calcium carbonate will not break down at room temperature. But if I take that calcium carbonate and I put it on mercury, on the side of mercury that's facing the sun where it's really hot, then this reaction does break down. It actually breaks down about 780 Kelvin or something like that, and the side of the mercury that's facing the sun is way hotter than that. So this would be spontaneous at higher temperatures. So we can't just rely on our enthalpy change. We've got to come up with some other things, which we've talked about a little bit. Right, so we talked about the fact that enthalpy, right, can tell us, it probably is spontaneous or not. And we decided, okay, let's come up with another factor that we're going to call entropy, right? Remember that's our S, right, or entropy change, which is delta S. And what we find is that in nature, all around us, right, what we find is everything around us is trying to move from something that is spontaneous, right, is always moving, spontaneously, from something that is well ordered to something that is more random or more disordered. And one of the ways that we say this in chemistry is that we're going from a state of lower probability to one of higher probability. We'll see the probabilities mathematically in a slide or two, but really when we think about randomness, just think about whether something is really well ordered or whether it's random. What we find is that everything, if we leave it by itself, is going to go to as much disorder or randomness as possible. And as it says there, right, we're going towards a condition of maximum probability. That just means that we're going towards more disorder. Right? And one way that I kind of think about this is like, I think, okay, one way I like to think of it is like the Big Bang. Right? If we think about the Big Bang, like everything was tightly packed in one little area. So if you wanted to find every atom in the entire universe, you would know exactly where it was. It was at one little point. And then the Big Bang happened and everything started spreading out. Well, everything's now, if I wanted to find a specific atom, I once found it in one little point there before the Big Bang. Now it's spread out. It could be randomly almost anywhere. I got to go and search it out. Right? And so nature itself is always doing that. It's trying to be more and more random if it possibly can. Left to its own devices, it does so. So one really good way of thinking about whether something is random or not is looking at rolling dice. So over on the right-hand side, notice that I have a whole bunch of ways to roll a 7, right? There happens to be 6 possible ways to roll a 7. The first dice can be a 1, and the second one could be a 6. Or the first dice could be a 6, and the second one could be a 7. Those are actually 2 different ways to roll a 7 if you think about it. And then 2, 5, 5, 2, 3, 4, 4, 3. So there's 6 different possibilities of rolling a 7. But there's only one way to roll a 12. One way to roll a 12, 6 ways to do our 7 there. Right, and so what we say is that the state of 7 is of higher probability, right? It means that it's much more likely that if I gave you 2 die that you're going to roll a 7, then you're going to roll a 12, right? And so rolling a 7 then is actually more disordered or more random, right? Because you could have rolled a 1 and a 6 or a 6 and a 1. We don't know which one you rolled. If you tell me that you rolled a 7, it could have been one of those. It actually could have been 6 different ways that you got there. If you tell me that you rolled a 12, there's only one possible way you could have done that, and that's rolling 2 6s. All right, at the bottom, notice that there is a equation here, which has S. S, remember, is our entropy. And S in this case is equal to KB times the natural log of W. All right, KB is what we call the Boltzmann's constant. So KB is equal to 1.38 times 10 to the minus 23rd joules per Kelvin. All right, and W is our possibilities. All right, so what that means is that W for rolling a 7 is going to be 6, right? Because there's 6 different ways that I can do that. All right, so what I'm going to do is I'm going to calculate our entropy for rolling a 7 and rolling a 12. All right, so our entropy for rolling a 7, right, is going to be S is equal to our Boltzmann constant, 1.38 times 10 to the minus 23rd, and that's joules per Kelvin. All right, times the natural log of 6. All right, and when I calculate that, I'm going to get 2.47 times 10 to the minus 23rd, and that's joules per Kelvin. All right, that's a really tiny number, right? But let's do it for rolling a 12. S for rolling a 12 is 1.38 times 10 to our minus 23rd, right? That's still our Boltzmann's constant, times the natural log of 1, and the natural log of 1 happens to be 0. So the entropy for rolling a 12 happens to be 0. All right, the entropy for rolling a 6 is a really tiny number, but it's still bigger than 0 is. So notice that entropy increases the more random something is, right? So entropy increases the more random it is. All right, so another way that we can think about, right, the randomness of something is, let's say that we were going to take 2 different gases and mix them together, right? And so my example here, and what we're going to see on the next slide in a pictorial view, is let's say that I had a couple of flasks. I had one that was filled with hydrogen and one that was filled with nitrogen. And they were separated, and then I opened up a valve in between them to allow the gases to maybe commingle and mix. Right? Well, what happens is over time we're going to end up with a random mix of hydrogen and nitrogen on both sides of it. Right? If I've got these gases, it's not like I take the 2 gases and they just don't like each other and they're going to separate from each other. Right? The odds of that happening is really small. Them being randomly mixed together is a spontaneous thing. Right? If you think about the air that we're breathing in, it's mostly nitrogen and some oxygen and some other trace gases. right? But when you breathe in the air, it's not like you breathe in one time and it's all nitrogen, and then another time it's all nitrogen, and then the next time it's all oxygen. Every time you breathe in, you have a mixture of oxygen and nitrogen, because the mixing of them, having them being randomly mixed together, is much more likely than you walking through the room and having a random pocket of just nitrogen air in there. That's just not going to happen very often. So having them randomly mix is more likely, which is more entropy, higher entropy. So here we can see that if we have one of our places where we've got just our nitrogen, maybe those are the green spheres, and one side which is just our hydrogen, which is our red spheres, and then we turn our stopcock and down on the bottom now it's opened up, right? We're going to have a random mixture of them. We can let it sit there for as long as we want, and the odds of us coming back and just finding one side of it fixed with only nitrogen and one side only hydrogen is really, really small. The odds are that they're going to be mixed together. Right? That's what we mean, is that things are going to spontaneously go to be mixed like that because that's how they want to be. And that's going to likely then saying that the more random something is likely to be spontaneous because of this. Okay, so let's do a sample problem here in which we are going to talk about whether these different processes are going to be spontaneous based on, right, just the things that we can see around us, right? We're not having to do any math or figure them out, right? It's just kind of things like, does this make sense? So if you build a snowman, right, will it eventually melt? Like if you just leave it out in the sun, it might not melt that day, might not melt in a week, but if you came back in June, the odds are, right, probably will have melted, right? It melted. Right, so this is a spontaneous process, right? The solid is going to want to become a liquid as long as we end up above freezing. It's just like us putting our hunk of ice on the kitchen table and walking away. That's spontaneous. All right, next up is building a house of cards. All right, if anybody's ever built a house of cards, right, you sit there, you take two cards, and you put them in a V like this, and then you set them down on the table, and then they go whoop, and they fall down. Right? And then you get a couple of cards and you put them like this again and you try to set them up on the table and they might sit there for a second. And then, a dog walks by or a fly lands in another room and they go whoop like that and you're like, right? It's super annoying. You can't take a deck of cards and just throw them on the ground and whoo, a house of cards has built itself. Right? Building a house of cards takes a lot of effort. That is not spontaneous whatsoever. It just doesn't happen by itself. All right, and then sorting clothes in a laundry basket. I wish that I could do my laundry and then just, pull it out and all my socks would be all matched up and then I could just pair them up. And all my underwear would be sitting in one spot and all my, t-shirts would be all in another spot. No, you've got to sort through it, right? You've got to work at it. And so that's not spontaneous. You're actually putting energy into the system. It doesn't just happen on its own. All right, another way of us to look at this as sample problem 20-2 is by thinking about our own experiences. Let's figure out whether we think the following reactions are going to be spontaneous or not. So first off, I have solid carbon dioxide, right? So solid carbon dioxide can sometimes be called dry ice. All right, dry ice is something that sublimates at room temperature, and this problem is at 25 degrees Celsius room temperature. So sublimation is going from a solid to a gas. Does that happen all on its own spontaneously at room temperature? Sure it does. If you got a piece of dry ice and set it on the table and come back, it's going to disappear after like 10 minutes. It's going to be gone. So that's spontaneous. All right. Sodium chloride, table salt, right? That's a solid at room temperature. Does it just miraculously turn into a liquid at room temperature? Well, based on our experiences, probably not, right? I have some salt sitting upstairs that's probably been in the container for like a year. It's not just turning into a liquid up there. Right now I can dissolve it in water and stuff like that, but just the solid, right? I don't come back to my salt shaker and all of a sudden I got like a hunk of salt floating in some sodium chloride liquid. That doesn't happen. So that's non-spontaneous. Part C is table salt again. Does it break apart into sodium and chlorine gas? Again, no. If I have some salt in my salt shaker and I come back in a year, I'm going to have the same amount of salt in there. I'm glad that it doesn't break into sodium because sodium is a reactive metal, right? It reacts with water and it would burn. And chlorine gas is not good either if you huff that in. It turns into hydrochloric acid in your lungs and it'll kill you. So I'm glad that this does not spontaneously break apart into the elements like that. And then the last one down there is carbon dioxide. All right, carbon dioxide is one of the greenhouse gases. It's one of the things that's in the atmosphere all the time. Does that break into carbon and oxygen? All right, well, if it did, it'd be nice to have some extra oxygen around. That doesn't seem so bad. But it would also turn into that solid carbon, right, which would be graphite. And so we would constantly have a layer of graphite all around us, right? And so we would have to be sweeping up graphite from the floors on a daily basis. So this does not occur. So that is non-spontaneous. All right, this ends probably the longest of the podcast of this chapter. I'm sorry it was long, but it's a lot of stuff to get through on this chapter. Right. On our next one, we're going to start to introduce, right, our entropy in a little bit more in-depth way of seeing how we're going to calculate that mathematically. All right, I'll see you then.